Hello and welcome back to another lecture on Chapter 17. We're just getting started here, so this will be an introduction. And the lecture will cover a number of topics, primarily related to moisture in the atmosphere and how that moisture behaves, where we find it, and how we might be able to predict how much is there, as well as kind of the features that we see that are associated with moisture. So I'll focus mainly on something called relative humidity in this introductory lecture. We'll talk then later on about cooling and condensation. We'll go on to talk about clouds, and then finally wrap up with precipitation to wrap up Chapter 17. So what is relative humidity? We're experiencing it in Illinois right now. You go outside and it feels a little hot, a little sticky, a little uncomfortable. That's the moisture, atmospheric moisture, that is making us feel like that. And it has to do with a little bit with how we experience or condition our bodies in an environmentally humid environment. Usually we use sweat as a way of cooling, and what sweat will do is as it evaporates from our skin, it carries away heat, and that cools us off. It's called evaporative cooling. So when humidity is high, there's less evaporative cooling, and we feel hotter. So if you go for a run or do any kind of exercise, you really feel a lot less comfortable when there's high humidity. Now, we don't usually measure humidity in absolute terms. It's a lot easier to measure it in relative terms. And so what has been done is experiments have been done to look at how much moisture air can hold, and then we kind of evaluate using an evaporative method, something called a sling psychrometer that we'll use in lab, the relative humidity. So for any given temperature, how much water is present in the atmosphere, because the atmospheric ability to hold temperature or hold water changes as temperature changes, and I'll talk about that a little bit more. So it's a measurement really then of the percent of moisture in the air, as I'm just sort of highlighting on the screen here. Moisture in the air is a function of temperature. Talk about that more. And then we've got the actual relative humidity, which is the actual water in the air, right, divided by, there's a little division symbol here, right, the maximum water that the air can hold times 100, and that'll end up giving us 100. That'll give us some sort of percentage from 0 to 100. At saturation, so that means the air holds as much as it can. We should always be at 100% relative humidity. And so we're going to think about air from now on as moving around in blobs or what we call parcels. It's just a volume of air, maybe 1,000 cubic meters of air that's going to move up or down. We can measure relative humidity in that parcel of air. So when I talk about a parcel of air, I'm thinking about a kind of a box full of air, a package of air, as we do some of these calculations. So here's a graph that's showing us water vapor on the y-axis and temperature on the x-axis in degrees Celsius. And when we see here negative 40 on the left and positive 40 degrees Celsius on the right, temperature increases, and we see that the water vapor in grams per kilogram of air, right? So that's kind of key, grams of water per kilogram of air. And we see that it increases exponentially. So that means that, at 20 grams or 20 degrees Celsius, for instance, right about here, the atmosphere can hold a maximum of about 17 grams H2O per kilogram. And if I'm down here at 0, it can hold about 3.5 grams of H2O per kilogram. Excuse me. And then if I increase it up to, let's say, 30, which would be right about here, 30 degrees Celsius, I'm looking at about 28 grams of H2O per kilogram. So it's not a linear relationship, it's an exponential relationship. The hotter the temperature, the atmospheric temperature is, the more water the atmosphere can hold. This is a table. It's just going to show us the basic relationships. I'm going to come back to this table in a number of slides here, but it shows us something called the saturation mixing ratio, right? That saturation mixing ratio is the maximum amount of water that the air can hold at a given temperature. So the mixing ratio then is just what the air has in it. I'm going to write that mixing ratio right here. The mixing ratio is what the air actually has in it, for instance, today. So let's say today we're at 90%. That would give us relative humidity is 90%. And so let's say the atmospheric temperature is at 30 degrees Celsius. So 86 degrees outside. It's pretty warm. I don't actually know. It might be a little cooler than that. And so 90% of that would be 90% of 26.5. And I'll do these calculations later on, but just to throw it out there, 26.5 is about 23.85. So the humidity, if we were at 90% relative humidity, today we would have actually 23.85 excuse me, grams in the atmosphere. That's the mixing ratio. And the air can actually hold 26. So we're under saturation. We're less than 100%. So the saturation mixing ratio is 100%. And you'll notice it is a function of pressure. It's what the air can hold at a given temperature. And if you were to take all these data points here, starting at 0.1 and negative 40 and plotting them up, you would end up with a curve that looks like this curve that I just got here, right? So this curve, and this, if I erase all these things, this curve here shown in blue, I'm sort of highlighting in red. That's the idealized curve. That's the saturation mixing ratio. Okay. All right. So what's really going on then with relative humidity? Typically, the air is not saturated. And so on the right-hand side, we have a situation where we have the atmospheric parcel. Remember I said a parcel is just a volume of air. In this excuse me. In this case, it's just an area. Here on the right-hand side, that area is larger than the vapor content, and so that means that the relative humidity at 30 degrees Celsius is going to be less than 100%. So the air can hold more water than it actually has in it. So here's your vapor content here, right? If we cool that temperature down to 20 degrees Celsius, we're going to reduce that air parcel, the amount of water that it could hold, right? That's just a function of temperature. So cool it down. We reduce the amount of water it can hold. What actually happens to the relative humidity, though, is the relative humidity goes up. What you notice, though, between these two volumes of water or areas of water, they're the same size. Okay, so in this case, we changed relative humidity going from 30 degrees down to 20 degrees Celsius, but we didn't actually change how much water is in there yet, and that's an important concept. You don't have to add water to change relative humidity. You just have to change the temperature of the air. If I want to take it down to 100% relative humidity, I got to decrease the temperature. Yet once again, notice the water content between these two diagrams is the same. So we're at 10 degrees, and the relative humidity has gone up to 100% relative humidity. All right, so how do we calculate relative humidity? It's pretty straightforward. It's going to be simply the mixing ratio divided by the saturation mixing ratio. Both of these are in grams per kilogram of atmosphere, grams of H2O per kilogram of atmosphere, or kilogram of air. So this is also grams per kilogram, right? And so what happens when you divide grams per kilogram by grams per kilogram, actually all these units cancel out, so the tops and the bottoms here cancel. And so if we were to take this and do this calculation at a particular temperature, let's say we're at 15 degrees Celsius, 15 degrees C, and let's say we have 5, the mixing ratio in this case, the mixing ratio is at 5 grams per kilogram, right? And so let's say our temperature then is at 15 degrees Celsius. We're going to come over to this diagram. You could do this on the on the plot as well. Find 15 degrees Celsius, and what's the saturation mixing ratio? Well, it's 10. We're holding 5 right now, so 5 divided by 10, right, times 100 is equal to 50%. Right, so you're at 50% relative humidity in that case. Now, let's say we wanted to, we cooled things from 15, we cooled them from 15 to 5 degrees Celsius. Well, we could redo this calculation. We know we have the same amount of water in the system. That water is 5 grams, so we'll start with 5 grams in the numerator here. And then we're going to cool it down to 5 degrees Celsius. So we're going to go over to temperature here. At 5 degrees Celsius, how much water can the atmosphere hold? What's its maximum? What's its saturation? It's at saturation at 5 grams per kilogram. So we'll times 5 divided by 5 times 100 is equal to 100%. And we'll do that as RH. That's just for relative humidity. That's RH, right? So in the first problem, we calculated that at 15 degrees C, we had 50% relative humidity. All we did was cool the temperature of the air, our parcel of air, or volume of air, down by 10 degrees, and relative humidity goes up by 100 without adding any water to the system. Now, there are situations where water does get added to that parcel of air, that package of air, and they'll come up sporadically as we move through the rest of the lecture materials. So if we want to visualize this maybe in another way, we can look at relative humidity, and we're keeping the temperature constant, right? So this is where we're just adding water to the system and not changing the temperature. So if we come to the left-hand side of this diagram, we're at 25 degrees C, and the saturation mixing ratio, the maximum amount that the air can hold, is 20 grams per kilogram of 20 grams of H2O per kilogram of atmosphere. We'll say that there's 5 grams in the system, and so 5 divided by 20 gives us 25%, right? We increase the H2O in the system. We just add water to it, all right? So we're going to add water to it. So we're going to jack this from 5 to 10 grams per kilogram. We're now keeping the saturation mixing ratio at constant, right? Because temperature stays the same, so the saturation mixing ratio stays the same. And that means 10, down here at the bottom, 10 divided by 20 gives us 50% relative humidity. Now here on the next far right, we're gonna keep, again, the temperature is 25. Temperature's 25. The saturation mixing ratio doesn't change, but at 25 degrees Celsius, we know that it can hold 20 grams per kilogram, and we're at 20 grams per kilogram in terms of how much water we've cranked it from 5 to 10, from 10 to 20, and so the calculation then yields 100% relative humidity in this environment. So holding temperature constant means you're holding the saturation mixing ratio constant, and the only way in that case to change relative humidity is to add water to the system. So here's an example where we're going to change temperature. We've already done another version of this a couple slides ago. We start out at 20 degrees Celsius. We're going to go down to 10 and then down to 0. Excuse me. And we're going to hold the amount of water constant in the system. So we're going to start with vapor. We're going to start at 7. We're going to decrease the temperature here by 10 degrees. So if we start at 7 grams of water, and we're at 20 degrees. Well, at 20 degrees, we can hold 14 grams. We have 7 grams, so 7 divided by 14 times 100 ends up giving us 50% relative humidity. We cool the temperature down, but we don't change the grams at all. So now the saturation mixing ratio changes because we've changed the temperature of the system. At 10 degrees Celsius, we're down to 7 grams per kilogram, 7 grams of H2O per kilogram of atmosphere. H2O then in the system is still at 7 grams. And so 7 divided by 7 equals 100%. In the next one, the last one here, we're gonna reduce the saturation mixing ratio even further. So we're going from 20 to 10. Now we're down to the last diagram here, 0 degrees. At 0 degrees, the air can hold at its maximum 3.5 grams of H2O per kilogram of atmosphere. So if we cool it to 0, we're actually cooling it down to the point where we have to subtract some water from the system, and that water is going to then come out as a liquid, right? So we had 7 grams in the atmosphere. We cooled it to the point where the atmosphere can only hold 3.5. 3.5 minus, or 7 minus 3.5 gives us 3 grams of extra water. This is excess. Okay. How does that come out of the system? It comes out as rain or precipitation, and then we're still at 100%, right? So it's sort of like in this last image, it's like we've taken a sponge and we wrung out some of the water in our sponge, but the sponge is still very wet. It's still at saturation, okay? All right, so calculating the excess water is actually a pretty easy calculation to do. Let's say we're at 25 degrees Celsius. Okay, what's the saturation mixing ratio? We'll come over here at 25 is right there. So saturation mixing ratio is 20 grams per kilogram, grams of H2O per kilogram of atmosphere. And let's say our mixing ratio, just for the ease of doing this, the mixing ratio is equal to 20 grams per kilogram. So the air can hold 20 grams at 25 degrees Celsius, and we're at 20 grams per kilogram in our current parcel of air. And so that means 20 divided by 20 times 100 is equal to 100% RH in this example. And we were going to cool the atmosphere down a little bit. So we're at 25. We're going to cool to 15 degrees Celsius, right? So we're losing 10 degrees. So now we need to go over here and look at our table and say, well, all right, at 15 degrees Celsius, which is right here on the left-hand side, what's the saturation mixing ratio? Now the sat ratio, I'll just call it sat right here, is equal to 10 grams per kilogram, right? And so we have 20, right? So that means that we're going to lose how much? Well, it's going to be 20 grams per kilogram minus 10 grams per kilogram is equal to 10 grams per kilogram, right? So it's actually a really easy calculation. This is what we had. Okay, this is the previous temperature. This is the cooler saturation mixing ratio that we're cooling it down to, and this is the remainder here from subtracting that to is the excess grams of H2O per kilogram that we're going to lose out of the system as rain. Okay, that would be an example. Goes to liquid water. Now, there's one more thing to think about here. It's actually a really easy thing to think about, and that is what is the dew point in one of our systems. So we've already know what this is actually. We talked about it as the saturation or at saturation, right? So dew point is at saturation, and saturation is equal to 100% relative humidity. Okay, so we just simply need to know when we've got 100% saturation in the system, or we've got 100% relative humidity, and and that means that, that dew then on a surface, we might be able to collect drops of water on a surface because the air is saturated in H2O. So we got our H2O drops here and here on whatever surface this is. It could be a leaf, it could be your car in the morning, it could be a building, a window. Any of those things would be places where saturation or moisture would collect. Actually, if you're listening to this and drinking a frosty beverage, if you had ice cubes in a cup of water, it's a good example of what's going on locally around what your cup. If I draw your cup here, here's your frosty beverage, right? There's your drink, and then inside there are ice cubes. Well, locally, what happens at the margins in this area, on the margins of the cup, is that the temperature inside the cup cools the atmospheric temperature, and you end up forming little beads of sweat on the outside of the cup. Those little beads are actually moisture that has been taken from the atmosphere and deposited on the edge of the cup. Why is that? Because the fluid in the cup and the ice has cooled the atmosphere locally right next to it in a very thin little envelope around the cup, and is, in some ways, maybe you could say, sucked water out of the atmosphere and deposited it on the cup. Okay. Anyway, this calculation is a really simple one. If we're at 35 degrees, C in our system, and let's say our mixing ratio is equal to 5 grams per kilogram. Okay. The question is, so we're at 35 degrees C. So let's come over to our chart here. 35 degrees C is right here. How much air or how much water can the air hold? It can hold 35 grams per kilogram, which is quite a lot. And we're going to cool things down to where we want to hit the dew point. Well, what tells us, where to stop? What temperature tells us where to stop? Well, dew point's at saturation. So the question is then, if our mixing ratio is at 5 grams per kilogram, where is our saturation mixing ratio? Also at 5 grams per kilogram. And so we need to cool it from here, 35, down to where our saturation mixing ratio is 5 grams per kilogram. And that turns out to be 5 degrees Celsius. 5 degrees C is equal to our dew point. All right, so that's dew point temperature, actually, and that's simply the temperature at which dew will form, or the temperature at which it may form, and the temperature at which you reach saturation in your mixing ratio. Okay, so that wraps up an introduction to Chapter 17.